Okay, so good morning, everybody. Thanks for coming. And again, I apologize for the delay on my part in starting the class. There was a bit of a ruckus at home. Of course, there's no excuse or a good excuse, especially since I'm the one always telling you all to come to class on time. Anyways, so till now we have been talking about discrete symmetries. I'm sorry, continuous symmetries, right? And in these continuous symmetries, what we have is examples of these symmetries include the translations, rotations, and the reason we say that they are continuous is because the action of the symmetry is associated with some parameter, right? So that parameter labels, like tells you how much of that symmetry acts on the system. So as an example, if you say that you have the translation operator, and the translation operator is, let's say, given by right. So if you say that the translation operator, for instance, is given by this expression, then this has a parameter delta x, right? So delta x labels how far you want to displace your system, right? And delta x is a continuous variable, right? Because these are translations along the real line. So we call it a continuous symmetry. Another way to say the same thing is that, so let me write it down. Symmetries correspond to groups, right? So associated with the action of any symmetry, there is a group, right? So for instance, for translations, there is the translation group. For rotations, right? Yes, this is somewhat obvious. Then for boost, right? What is a boost? Now you remember that when you have a Lorentz transformation, a boost is a change in the velocity of an object, right? So you have a certain subset of the Lorentz group. So you have this group which is called the Lorentz group, and a certain subset of that Lorentz group corresponds to boost. And if you combine rotations and boosts together, these form the Lorentz group. Okay. So now I haven't really talked too much about groups or group theory, but I suppose that you probably have some exposure to these concepts, right? Then and these are all examples of discrete continuous symmetries. So these the groups are also continuous groups, right? So these are continuous symmetries associated with continuous groups. And groups of this kind also go by the name of Lie groups, Lie. So it's pronounced Lee. It's after a gentleman called Sophus Lee, who was one of the who studied these groups. And then what we have is we have discrete symmetries. So discrete symmetries correspond to discrete groups, right? So you have parity, time reversal, charge conjugation, and all three of these are discrete symmetries, and the group associated with all of them is called something called Z2 or Z2 if you prefer the Indian pronunciation. So Z2 is a group of two elements. You can call them anything you like. You can call them 1, -1, or you can call them A and B, or you can call them 0 and 1. It doesn't matter. What matters in a group is the multiplication table. So in a group, what you can do is you can take any two elements and you can, well, I might as well tell you what a group is since we're on that. Actually, no, I think I've talked about groups in the first semester, right? Am I right? Can somebody please tell me if that's the case? Remind me if you're already familiar with the notion of a group.
So you mean like algebraic groups?
Sorry, I can't hear you.
Is it the same as groups in algebra?
Yeah. Of course, these are groups. But did I not talk about groups in the first semester?
No. Yes. No.
No. So how many of you know what a group is? Can you just raise your hands if you know what a group is? Or just say yes or no? No. So nobody's raising their hands or saying anything. Okay, all right. So I will give you the necessary introduction to groups. Okay.
Sir, I don't think it was discussed in the first sem.
Did I not? Okay. Because I discussed rotations and angular momentum in some detail, so I thought that maybe I must have discussed the notion of a group also. Okay. All right, no issue. So we'll talk about that, since that is essentially how you characterize symmetry transformation. Okay. Groups. So what is a group? A group is a set, right? It can be a finite set or an infinite set. Which is closed under something called a group multiplication operation. Okay. So as an example, I'll give you a couple of examples first. Then I'll give you the axioms of a group. Example is if you consider the set of natural numbers, right? So the set of natural numbers. Yeah. So the natural numbers is contains is a set of non-negative integers, right? So some definitions include 0, some don't. I'll include 0 since we need it for the definition of this. And the multiplication operation in this case is what we refer to as ordinary addition. Okay. So for any two elements, right, A plus B, we get a third element, C, which also belongs to the natural number. Right? Then there is something called the identity element. Every group has to have an identity element. In this case, our identity element is just the number 0. So if you take 0 and multiply it, multiply meaning the group multiplication, not ordinary multiplication, you get the same number back. Now, a group also needs to have an operation which is called an inverse. So an inverse means that if I have any element of the group, there should exist another element of the group which I denote by A inverse, such that the multiplying the two gives me the group identity. In this case, 0. So in this case, group multiplication is just addition of numbers, identity is 0. Now, if you will notice, this is actually not complete under the inverse operation, because in order to take the inverse operation, I need to take the negative numbers also. So this is Z, the set of all integers. And now this set is closed under all of these operations. You can take any two integers and you can add them, you get a third integer. You can take any integer, add 0 to it, you get the same integer. You can take any integer and it's negative, add those two and you get 0, right? So the way we would write this down is that we say this is the group. We say what is the multiplication operation and what is the identity. This is a group of integers with addition as group multiplication, and 0 as the identity element. Okay. So is it, yes.
So just to clarify, a group is defined also by the operation under which it is closed.
Sorry?
So a group is defined by the operation under which it is closed.
Yes.
Okay,
The operation needs to be defined.
Fine.
You need to specify which operation you're talking about.
So if it was, in this case, suppose it was multiplication, that is, it would be a different group.
Then so if you take multiplication, right, then under the multiplication operation, the group of integers is closed. For example, I can take any two integers, multiply them.
And the identity would be 1.
The identity would be 1. But what would be the inverse? Right? So if I give you any integer n and I tell you what is the inverse of that integer, then that would not be an integer, right?
Yeah.
So that would be something that belongs to the rational number. So the next group that comes up, if you say that numerical multiplication is your set of operations, then you have to expand your group to include the this fractions. Okay.
Got it.
Another group, a very simple group, is but very important in physics, is called U1. What is U1? Well, it is the group of complex numbers with norm equal to 1. So basically, it's the group, it's a set of elements in the complex plane which live on this circle, right? So any such element I can write as e to the I theta, right? Any element on the circle, unit circle, okay? It's just a phase. Now I can take any two, if I take any two of these numbers, if I take I theta 1 and I theta 2 and I multiply them, the result is again a third element on the unit circle, right? So if I take the unit circle in the complex plane, which is written as this math bold C, with your multiplication and the number 1 as the identity, then this becomes a group, right? And so for any element, there's also a unique inverse, which is just given by e to the minus I theta, right? Now I'll tell you in a second why it's called U1. Okay. The U here stands for unitary. Okay, so I'll explain that in a little bit. Then we have another group which is called SO2. Group of rotations in the two-dimensional plane. Okay, so what are the rotations in a plane? You have x and y, and I perform a rotation to different coordinates, x prime and y prime, right? Then how are the two coordinates related to each other? I can write the relation like this, right? Again, this is something that I hope all of you have seen. So this object, let me call this r theta, right? So it's a matrix. It's a 2 by 2 matrix, right? And now let me consider what happens if I perform two different rotations. So if I perform two rotations, right? So, and let me write this as r prime, right? So r prime is equal to r theta times r, right? So this is a matrix. R is a vector, r prime is another vector. Then I perform another rotation. using and the second rotation will correspond to some angle theta prime, and the relation between the vectors will be the same, right? Now, if you ask what is the relationship between the second set of transform vectors and the original set that you started out with, well, you can just substitute this expression for r prime in this expression, and you get this expression here, right? So now I'll leave it for you as a very straightforward exercise to show that if you multiply any two such matrices together, you get a third matrix, which is also a rotation matrix, which has exactly the same form, only with the parameter, the angle, being the sum of the two angles, right? So maybe you don't even need to do this, like maybe you have done it before. And then similarly, one can show that if you take r of minus theta and you multiply it by theta, what do you get? You get the identity matrix. I'm just writing this so that it's clear that this is the two-dimensional identity matrix, right? So this is a group now. What is the identity element? The identity element is just the identity matrix. The inverse is given by this expression, r minus theta. And the elements of this group are 2 by 2 matrices, right? But not any arbitrary 2 by 2 matrix, right? These matrices have some special properties. What properties do they have? So as an example, let me write down r minus theta. So if you take r minus theta and you put in this expression for r theta, you put theta is equal to minus theta, what do you get? Cosine remains the same. Sine will pick up a negative sign, right? Sine theta. So you will get cosine theta, sine theta minus sine theta, cosine theta, right? But now if you compare it to the original matrix, you can see that this matrix is related to r theta by a transposition operation, right? Transpose. We are taking if you take a transpose of this, the minus sign on this will go to the other element across the diagonal, right? So, and this matrix is also the inverse of the original rotation, right? Because when I multiply this object with r of theta, I get the identity. So such a matrix which satisfies this condition is called an orthogonal matrix. So an orthogonal matrix is one for which M transpose is equal to M inverse. And this letter O for orthogonal, this is what the O in SO2 represents. O is for orthogonal, right? So you have the set of 2 by 2 orthogonal matrices. But there is one more restriction on these matrices, which comes from this S. S stands for special. And what it means is that the determinant of the matrix is equal to +1. Again, you can check that very easily. You take the determinant of this matrix, it will be cosine square theta plus sine square theta is equal to 1. So this is the group of special orthogonal 2 by 2 matrices. Is this okay? If you have any questions, please ask me, okay? Now I can tell you why I refer to this as U1, the set of complex numbers. The reason I refer to this as U1 is because you can think of this as the set of 1 by 1 matrices. And what is the meaning of unitary? So let me define unitary while I'm at it. Unitary means that if you take a matrix and you take its adjoint. So the adjoint is the transpose of the complex conjugate or the complex conjugate of the transpose, either way. And for a unitary matrix, this is equal to the inverse of the matrix. And this is something that you already know, right? Because you remember in quantum mechanics, you have unitary operators. What is the property of a unitary operator? It's exactly this, right? Now, the group SO2 is isomorphic to U1, right? Now, this statement, you can see that this statement is true just by looking at, well, what is U1? U1 is the group of rotations, right? You're just rotating in the plane. And that's exactly what SO2 is. They're doing exactly the same thing, right? But if you want a one-to-one mapping of the elements, you can do that. An element of U1 is given by e to the I theta. An element of SO2 is given by R theta, right? So there's a one-to-one mapping between these elements. And there's a one-to-one mapping between the inverse and also with the identity. So here the identity is just a number 1. Here the identity is a 2 by 2 matrix. Right? So these two are the same group, just with a different name. Okay. Any questions so far? Okay. Now let me give you an example of a discrete group. Okay. So I've already mentioned this earlier, so I'll just use this example. The smallest discrete group is a group of 2 elements. You can write them as -1 or +1, it doesn't matter, or you can write them as A and B. And the multiplication table, the group multiplication, is as follows. So for a discrete group, we write down the group multiplication in this way. For a continuous group, it is not possible because there's an infinite number of group elements, right? So this is the group multiplication. AB is equal to A, BA is equal to A, and BB is equal to 1. This is the group multiplication, right? So you can easily see that if you just look at -1 and +1, and with your group multiplication as just your ordinary multiplication, right? -1 times -1 is +1, -1, -1, right? So this is a group with multiplication, and your identity is just this element B or +1, right? This is a very trivial group. We can consider a less trivial group by going to the something which has 3 elements. Okay. So as an example, okay, but before that, let me also point out that Z2, instead of writing using multiplication, we can also use group addition. We can use numerical addition as a group multiplication. But we have to use addition modulo 2, mod 2. Okay. And we have to write the group elements as 0, 1. So if you take 0 and 1 with addition mod 2, what do you get? 0 plus 1 mod 2 is 1. 0 plus 0 mod 2 is 0. 1 plus 1 mod 2 is what? Anybody? What is 2 mod 2?
0.
Right. And 1 plus 0 mod 2 also is 1. Right. So these 2 elements with addition as the group operation, addition modulo 2 as the group operation, these form a group. Right. The identity element is again 0. Right. And the inverse of an element. So here the inverse of 1 is just 1 again. Right. Another group which is very important is called Zn. So we'll write it like this: n minus 1 is the set of integers, the first n minus 1 integers with 0, with addition mod n as your group multiplication, and 0 as the identity. So as an example, let me look at, let's say, Z4. That is 0, 1, 2, 3. Right? So you can, it's clear that if you take any of these elements and add them to anything else, so if I take, let's say, 3 plus 3 mod 4, what do I get? Anybody?
2.
I get 2, right? Similarly, and so this belongs to Z4, right? Now, what about the inverse? What about the identity? The identity is just 0. What is the inverse of 3, let's say? The inverse of 3 is the element 1. The inverse of 1 is the element 3. The inverse of 2 is 2, and so on. So each element has an inverse, right? So again, this is a group. And so Zn is the group of, is the same group, but with n being so any arbitrary integer. Another group which is very important is the group of permutations of n objects. And this goes by the name of Sn. It's a symmetric group. So again, I will leave it as an exercise for you. Write down the group elements. What is the group multiplication? Identity and inverse for Sn. So it's a set of permutations of n elements. So the group multiplication is simply the permutation action, right? So you can start from the way you write down a permutation is as follows, right? You say 1, 2 till n. These are your n elements. And then, for instance, you have 4, 3, something, something, 7, something like this, right? So this corresponds to an element of the permutation group. It's telling you that 1 goes to 4, 2 goes to 3, and n goes to 7, right? This is the permutation. And then if you have another permutation which acts on this, it will, do the same thing. You will have, let's say, 4, 3, and whatever, 7. You have another permutation. It will take these elements to whatever other values you might have. 5, 4, 1. I mean, it just depends on what the size of your group is, right? So these are some examples of continuous and discrete groups. And now,
Excuse me,
let
sir.
me, yes, please.
Sir, I didn't understand the inverse for Z4.
The inverse for Zn, right?
Yes, sir.
For this one, the inverse is, so addition is modulo n, right? So you understand what that means, right? Modulo n means
Yes, sir.
you take the remainder.
We get the remainder. Yes.
So the identity is the 0 element, right? So 3 plus 0 mod 4 will just give me 3, and so on. I want the inverse. So I want the element such that 3 plus that element gives me 0, right? So for any element k, what is going to be the inverse? It's going to be n minus k. Why? Because k plus n minus k, mod n is going to be what?
0.
Right. Is this fine?
Yes, sir. I got it.
There are many other interesting groups, and there are some other aspects of groups, very important aspects which I haven't mentioned. So let me mention those two. So groups can be divided into two broad categories. One category is called an abelian group, other is called a non-abelian group. An abelian group, and this is named after a mathematician named George Abel, who died at a very young age, and he died in a duel because was that Abel or was that Galois? I forget, but he also died very, very young. So in an abelian group, if you take any two elements, the group multiplication is commutative. So the order of elements doesn't matter. In a non-abelian group, this is not true, right? So an example of an abelian group, for instance, is U1, SO2, or Zn. These are all abelian groups, right? An example of a non-abelian group is this thing, Sn right? Because two permutations will not, depends on the order in which you apply those permutations, right? You won't get a the third permutation depends on the order in which you apply the first. Then SO3. Now, what is SO3? SO3 is now you can read off from this. What does the S stand for? So first of all, what does the 3 stand for?
3x3 matrices.
3 by 3 matrices. What does the O stand for?
Orthogonal.
Orthogonal. And S stands for?
Special.
Special.
Determinant 1, right? So it's a group of 3 by 3 orthogonal matrices with unit determinant. And this is actually also the rotation group in 3 dimensions. Okay. Now, so this will be important for us when we talk about angular momentum in the next section. So rotations in 3 dimensions, in 2 dimensions, rotations form an abelian group, right? You can take any rotation and another rotation and then combine those two in any order, you will get the same rotation, right? Because of this fact, right? R theta times R theta prime the result is just R theta plus theta, right? But rotations in 3 dimensions are not commutative. And you can convince yourself by taking any 3-dimensional object, like this cell phone, for example, and applying 2 rotations to it. Let's say I apply a rotation to this cell phone around the vertical axis, and then I apply a rotation to it around the horizontal axis. Right, so I get this. Now my screen is upside down, so I just let me so I apply one rotation like this, another rotation like this. So I get this upside down screen. Now if I start with the same thing and I apply this rotation first, right, and then I apply this rotation, I get the same screen, but with the orientation change. You can check it. Maybe this is not the most. If you do it yourself, you will see it comes out to be the case. So rotations in 3 dimensions are not commutative. So this forms a non-abelian group. Okay. So now let's see. So this, what do you call it? Sakurai's treatment of symmetry is a little bit involved. So for the symmetry, discrete symmetries, I would recommend looking at the reference I've given you, David Tong, right? Topics in quantum mechanics. So I'm going to refer to that. And so we'll talk about parity. What is parity? That is the first discrete symmetry. Parity. Well, parity is simply taking your coordinates and saying that x goes to minus x. Okay. So now this is parity in position space. You can also have parity, let's say, in momentum space, right? So in parity in momentum space would give you p goes to minus p. You can have parity in phase space also, and in phase space you would have parity minus x. Okay. So as a very simple example of how parity works, let's consider a function. So just an ordinary function, any ordinary function, right? Doesn't matter, of some function on the real line. And let's say f of x is equal to sine of x. Now, if I apply parity to this function f of x, what do I get? I get f of minus x, right? Now, there are two possibilities. One possibility is that f of x could be equal to f of minus x. The other possibility is that f of x is equal to negative of f of minus, right? So as an example, what about sine of x? Sine of x comes in this category. Right, it's equal to minus sine of minus x, right? Sine of minus x will give you minus sine x, minus of that, right? So it's a negative of sine of x. An example of a function which satisfies this property is cosine of x. So this is referred to as even parity, and this is referred to as odd parity. Right. Now, if you have an arbitrary function, that function may or may not have even or odd parity, right? So, for instance, if I take some arbitrary function like this function has neither even parity nor odd parity. But what I can do is, given any function, I can construct an even part and an odd part just by taking linear combinations of f of x and f of minus, right? And then exercise, show that the parity operator acting on this function will just give you plus or minus of that function, right? So I think this is something that is straightforward to see. Okay, now why do we care about parity in quantum mechanics? The reason is as follows. Okay, so let me give you first an example from classical mechanics. Parity in classical mechanics. Okay, let us consider something like the angular momentum of an object, right? So I have some object, it's spinning, right? So I would say that the angular momentum points in this positive upwards direction, the z along the z-axis. Now, let's say there is a mirror okay, and I take a reflection of this object in that mirror, right? So when you take a reflection of this object, it's easy to see that the reflection will also be rotating, but the sense of rotation has switched, right? So the reflection has an angular momentum L prime, which is pointing in the opposite direction to L, right? And why is this the case? Because when we take a reflection in a mirror, what we are doing is we are taking R2 minus R. Right? So when we take R2 minus R, what happens to L? L goes to minus L. You can see that in this expression. Okay. Now, and linear momentum, for instance, is not affected, right? Linear momentum under reflections doesn't change. So in quantum mechanics, you can have states which have either even parity or odd parity, okay? And now, how should the action of a parity operator be? So now remember that in quantum mechanics, you have states. So if you act on any state with an operator, you will get another state, right? Psi prime. So how should the parity operator act on a state? Well, the parity operator, if you act on psi of x, it should give you psi of minus x. Now you can see that if you act twice, let's say you apply pi square, what do you get? You get psi of minus x, and then you again get psi of x, right? So pi square is equal to 1, right? And what this implies is that pi is equal to its own inverse, and also that it's equal to its complex conjugate adjoint, right? So this means that the parity operator is both Hermitian and unitary. Okay. And yeah, I was wrong about the action of parity on momentum. No, that was fine. Parity on momentum. So if you ask what is the action of parity on a momentum eigenstate, what will be the action? Well, how do you write on a momentum eigenstate? In the position basis, you write it like this: e to the I px by h bar x dx, right? So this is psi of x. The component of this momentum eigenstate in the position basis. So if I apply the parity operator to this psi of x, what do I get? I get psi of minus, which is equal to e to the minus I px by h bar, right? Because in this exponent, you will just get a negative sign. And this object corresponds to the coefficient for negative momentum, right? So the action of parity on a momentum state will be given by this expression. Okay. Now I'll stop here for the day and we will continue in our next class. Okay. And the thing is that at this point, it might still not be clear to you why we care about parity or time reversal. So the reason is because, I hope it's clear that why we care about symmetries in the first place. Symmetries tell us about the redundancy in the description of a system. Right? So if I have a system that is rotationally invariant, then I can pick any orientation and the system will be the same with respect to that orientation. Right? If a system is translationally invariant, then I know that I can move the system to any location, it will be the same. Right? So similarly, if a system has some behavior under parity, then I know what the what quantum numbers I can assign to the states of that system. Right? And there are many interactions in physics which either obey these symmetries or they don't. So what happens is that if you introduce, for instance, a magnetic field into a given system, you will find that under the influence of that magnetic field, the system will lose time reversal in there. So, and this is not just some theoretical concept. It's something that is observed in the laboratory, and it allows us to classify different states based on their symmetries. So, for example, there is a phenomenon called the quantum spin Hall effect, and this is a very recent discovery. It was first predicted in 2007, I think, and then experimentally observed in 2008. And this quantum spin Hall effect can only be described if you understand the behavior of certain substances under time reversal symmetry. So, yeah, I'll stop there. Any questions? Any questions? Anybody? Yeah.